section, 12.2. It's to do with vectors. You've met in a very sort of a superficial way, I suspect, vectors in trig. So let's just get some of the jargon out the way and the vocabulary. Right, so what is a vector? Well, a vector is a directed line segment. And I'm not going to do what a lawyer does, where you say, what is a directed line segment? And they say, oh, a directed line segment is a vector, in which case you don't know nothing, right? Let's show you what a directed line segment looks like. You have a start, you have a finish of a line. That's the line segment. And there's a direction to it. So all vectors have a direction. In this case, going that way, right? And what's called a magnitude. And the magnitude of this particular vector would very often be written like that. Have you ever seen two little vertical lines around it? It looks like the absolute value, but it means the length, right? The magnitude is another word for the length. So a vector is basically a piece of a line and a direction. If I draw, and I'm trying to draw this, another line, same direction, same length, this guy is a vector and that guy is a vector. And as far as we're concerned, they are identical, because vectors do not care where you draw them, right? They're not like coordinates where you start at the origin, even although if people do that because it's convenient, vectors can be anywhere, right? We also have some other notation that you will see. Sometimes you use the letter U or the letter V, and you put a little arrow above it. Has anybody seen that notation for a vector? Right. You will see this notation in textbooks, but not when I do them, because I can't do them. Is that you use the letter U, but you just make it thick. It's like bold. In a textbook, vectors are very often just a thick U or a thick V or a thick W. And it's much more convenient to use that notation, would you agree, than calling it PQ. But you will see it also called, because I'm not sure of places to put this, PQ with a little hat above it. And you will also see vectors sometimes written with that funny little hat on. Has anybody else came across a notation in science or engineering for a vector that I haven't put in this list? You've seen at least one of these versions, right? So I'm not going to start jumping around picking all sorts of versions. So I'm telling you the one I'm going to use. I'm going to use the U with the little arrow above it, because to me that kind of makes me think vector. So that's how I'm going to write vectors down. And I might occasionally use this notation if it suits the story, right? But the funny hat one in the bold, I'm never going to use, because you'd never know I was doing bold unless I spent a lot of time on it. So a vector is basically a piece of a line, right, with a direction to it. There's another term that you're going to get, and a scalar is a number. And there is no direction associated with a scalar. So if you're being lawyer-esque about it, and I use two words to describe the motion of a car. If I tell you it's speed, that's scalar. If I tell you it's velocity, that is a vector. Are you aware of the difference between scalar and vector, right? I could tell you you're going 40 miles an hour. That's speed. But a vector would be you're going 40 miles an hour at an angle of 45 degrees, or you're going 45 miles an hour up the way, or 45 miles an hour down the way, or to the right or to the left, right? There would be an association in that story. And you know, you get the kind of things where you pull something this way and you pull something that way. Those are vectors, aren't they? So scalars and vectors. Nothing too unusual, pretty consistent with those who've seen more vectors than other people. Right. Next one is just a question from the homework, so I want to get that one right away. Oh, darn it in space. I want to make it bigger. And I don't have my make it bigger button. What's that? I don't want to create code. Go away.
Try Control+ on your keyboard.
Oh, shoot. Hold that thought. I'm going to try it. Right. So this is my guy. And you said Control+. Oh. Oh, this is cool. Let me do that again. See the things you learn in this class that you don't know you're going to learn. Thank you. That was cool. Okay, here is basically it's a diagram, but it's being used to represent lots of little vectors. Now, they draw a vector, it's a line, and the little arrow, the direction arrow, is at the tip. I like to put the arrow in the middle because you can see it better. It's a bit hard sometimes, especially when they meet in the corner, to realize that this is AB. Now, it says here, find another vector that's the same as AB. Would you agree that if you're going from A to B, which one of these other vectors mentioned below it is the same thing as it?
Charlie to Bravo.
Say again?
Charlie
Maybe
to Bravo. C to B.
You think C to B is the same as A to B?
Yes.
And does
Same
A to
direction, it's the same magnitude.
Well, I'm seeing C to B going up the way and A to B is going left and right. So I'm not seeing the same direction.
Oh, I was thinking D to A and
oh,
B to
okay.
C. I'm
well,
sorry.
D to A, I totally agree
blank.
with you. D to A is the next one. I'm trying to find the A to B one through this list. A to B, would you agree it's D to C? Right. And then the one you just gave was the answer to this one. And can you imagine the answer? Well, maybe you can't answer. This one's E to A. Let's see. Isn't E to A the same thing as C to E? You start here and you go here. They use the word displacement, which basically is think of where you start and where you finish. Is there another journey that's got from a different start? Does it have the same kind of movement to the finish? So if I was looking EA, I'd be going like 4 left and 3 up. 4 left and 3 up, right? Same direction, same amount. Okay. Now, do you see that bold notation that they're using here? That is one of the vector notations. Find a vector A represented by this fella here. Okay, that's my signal to leave this now. So how do we represent vectors? How do we put numbers on them so that people can visualize them and to do sketches of them? So we'll do it with 2-dimensional and then move on to 3. Suppose I have the point 5, 7 and B is the point 3, -1, right? Just for argument's sake. And you want to do a vector AB. So if you can pretend that that's where A is, and can we pretend that that's where B is, would you agree that that vector is pointing downwards and to the left, right? Would you agree that's AB? Now, there is 2 main ways in which you describe a vector using numbers. The first one uses notation that looks like that. It looks like a greater than symbol and a less than symbol. They're nothing to do with greater than or less than, they're just symbols, right? And in this case here, the first number, whatever it's going to be, is called the X component. And the second number, whatever it's going to be, is called the Y component. And so what you imagine is that you start at A, and then you say, how many in the X direction do you travel? And then after that, how many in the Y direction you travel? And there is a formula for calculating it. So let's show you what it is. It's the X coordinate of B, take away the X coordinate of A, that's the X movement. And the Y coordinate of B, take away the Y coordinate of A, that's the Y component. So if we look at this guy, he's XA and he's XB, and he's XA, YA, sorry. He's XB and he's YB. There we go. So what we have is 3 take away 5. And we have -1 take away 7. And we have -2, -8. And that is our vector. So if you wanted to sketch this vector, can you imagine you could start anywhere you like? Because vectors don't care where they begin, right? They're all equally vectors. And then from this vector, you'd go 2 this way. That's what -2 means. And then can you imagine going 8 down? And that would be a drawing of this vector. Have you seen this notation that looks like funny brackets? Any of you seen that notation? Okay, so you're comfortable with that one, right? Now, there is 2 special vectors. Actually, there's 3, but right now we're only doing 2 of them. And they're called I and J. The vector I is 1 in the X direction, and the vector J is 1 in the Y direction. So this vector up here, right, this guy here, can also be written as -2I minus 8J. So we have 2, I guess we could call them competing notations for how to do a vector. And can you say that that's basically 2 to the left, so -2x components and -8y components? Does that seem reasonable? We go with that. Some questions want the answer in component form. Some questions want the answer in IJ notation. I think Grebesign's happy with both. I haven't tried it. I should, but I didn't, to see whether this notation works by putting in the less than and greater than symbol. I hope it does. It would just make life easier. I prefer this notation rather than that one, but that's just a preference. So that's what a 2D vector looks like. Suppose I wanted to find the components of the vector joining those 2 guys together. Now, I'm not going to even attempt to draw that picture because we know drawing 3-dimensional things in 2D paper doesn't work. So can we pretend that that's A to B, right? Yeah, pretend it's sticking out like that pen, right? You can get the vector joining A to B. It's x of B take away x of A, y of B take away y of A, and z of B take away z of A. And it's 7 take away 1, that's the x component. 1 take away 2 is the y component, and -3 take away 4 is the z component. And so this vector is 6, -1, -7. Are we comfortable with how you can find a vector that joins 2 points in 3D space together? Now, if I wanted to do that using ij notation, it's 6i, take away 1j minus 7k, because you can have I, 1 in the x direction, j, 1 unit movement in the y direction, and k, 1 unit in the z direction. Is that kind of consistent with the way that the others are created? Great. Now, we're not going to get into this, but it's kind of fun to talk about it. So let me talk about this. Right, got some people trying to come in. Why are they not coming in? There we go. This is a three-dimensional vector, right? I could just about visualize it. Isn't it like a pen? The base to the tip, right? And you orientate it. It'd be sticking in 3D, right? Can I have a point? Can I have 2 points in 5-dimensional space? Would you agree you could have any dimensions you like? And for those 2 points, couldn't I find the vector joining? What that means is that we've now created a system that can be generated, can be expanded to any number of dimensions that you like. I think that's pretty cool. And apart from the fact that they're bigger, there's not a big deal. Of course, I no longer know what that vector looks like. Would you agree most people can't think in 5 dimensions? And in fact, if they can think in 5 dimensions, they probably should seek help, because there's something wrong with their brain if they believe they can do it. Now let's introduce you to a rather strange vector called the zero vector. And in 3D, the zero vector is that, and it is called zero with a little arrow on it, right? It's a zero vector. I'm now going to draw the zero vector. Anybody tell me what I should draw to represent the zero vector?
Is it just a point?
There it is. There we go. There's the zero vector. Don't you start at any point you like, and then don't go left or right or anywhere in the Y or anywhere up and down. Just stay put. The zero vector is actually not just, it can be useful because it does allow us to do certain calculations. Isn't there a thing in engineering where you want to balance forces? Well, isn't balancing forces basically you add them all up and you should come to a zero vector? That's what balances them, right? So, the zero vector is helpful for those kind of things. Right. So let's return now to a homework question. Right, here's a little picture. Could be 2D, could be 3D, doesn't really matter. And we're looking at how to add or combine vectors. And A to B plus B to C. What single vector would be A to B plus B to C? A to B and then B to C. What single vector would represent that?
Is it A to C?
It is. Now I'm clicking on that and I'm hoping I can go here. And guess what? The funny little brackets are there. Good. But in this case, we're going to have to use that notation. And won't we just go A to C? Looks a bit yonky, but I'll take it. C to D plus DEB. Would you agree that one is also a vector? And what do? You start at C and you finish at B? There we go. Oh, this one's a bit sneaky. D to B minus AB. What is minus AB the same as? Well, what I'm getting at is it's the same as minus BEA, isn't it? Let's show you that then. If you look at a vector, let's look at what's called the negative of a vector. Right, if you've got a number 3, would you agree it's negative is negative 3? And if you've got a number that's already negative, isn't it negative plus 7, right? Well, vectors have this kind of process as well. If you have a vector, and let's write it down like that, and I'll call this vector u, right? The negative of u is that. Now, if you draw the vectors, can you imagine this is what vector u looks like? What will vector negative u look like? I've already drawn most of it, but what will the vector negative u look like?
It's going the other direction, right?
Yes. So essentially, doesn't the negative just reverse the direction of the vector? So instead of going up the line, you come down the line, right? Now, if you're doing vectors that have letters associated to them, like those kind of vectors, right? The negative of AD is actually DA. Does that make sense? Same guy, but go up the line instead of come down the line. So if you are being asked to do a journey, combine two journeys together, you will say, oh, the negative of that is the same as that. Oh, have you noticed that you want these to be the same? Because if you do a journey to B, you want to leave from B to go to the next town. And when you do that, isn't it just the start and the finish that tell you your journey? Right. Here's a weird long one. What would that journey be the same as?
A to P.
Yeah, it looks like a P, so I'll pretend I meant a P. Yeah. Agreed. Now, couldn't they stick in a couple of these guys? Oh, B. Do you notice these two guys that are negative, right? If you switch their direction, don't they turn into these guys and the answer's still A to P? That makes sense? Right. What about this journey? What vector would AB plus BA get you?
A.
And what's another name for the vector A to A?
Zero vector.
So wouldn't a zero vector be kind of like a round trip where you start someplace but you end up at the place you started? That would be a zero vector. Right. So let's look at now. How to add vectors that actually have components, right? So not A, B, and B, C, but vectors like this. Suppose I have a vector U, and it's 1, 3, 5, and I have another vector, I'll call it V, and it's 2, -1, 6. It would be nice if we could find a way to add two vectors together, you know, like AB plus BC kind of thing, right? Be nice if we could do that. The rule for doing it is remarkably straightforward, right? Intuitive, I would call it. Would you agree that the most likely way to add two vectors together would be to add their X, Y, and Z components together, right? Well, that seems, and that's exactly what you do. So you add them, and you get 3, and you add these, and you get 2, and you add these, and you get 11. Now, if you want to imagine what on earth does this look like visually? Well, can we pretend that this is the vector U, right? It starts off here and it finishes here. When U finishes, you have another vector, V, and V does this. U plus V is that red vector. So by adding the components, don't you basically just make a little triangle where U and V make the two sides, but the sum is start to finish, right? It's a bit like, I could take the scenic route or I could take the motorway, right? I could go straight to the other place. And U plus V represents this. I believe it's sometimes called the triangle of forces for the people who are in engineering. Have you seen triangle of forces term or something similar to that name? But would you also agree it's dead easy to add, even if you've never seen a vector in your life? Isn't adding their components a pretty intuitive thing to do? Let's look at how to subtract vectors then. So let's have a vector U, 1, 3, 5 again. And let's have vector V, and it can be 2, -1, 6 again. If life was fair and mathematics was logical, how do you think you should subtract two vectors? I hope the question is so easy that you don't want to answer it in case there's a trick. Let me tell you, there's no trick.
Just subtract the individual components.
Yeah. In this case, -1, 4, -1. Check that. Okay. Now, visually, what does that look like? Well, if I'll try and be as accurate as I can, there's U. Now, this vector here is V. We think of subtracting vectors as adding the negative of the vector. So if this is U, oh, damn it, I should have done it lower down, right? If this is U, if V goes this way, if this is the vector V, won't the vector -V go that way? And this vector then is what U take away V looks like. So we think of adding and subtraction as really the same process. Adding, you just add the two vectors together. Subtraction, don't you add the negative of the second vector? And so when you look at these, would you agree that U minus V is quite a different looking vector than U plus V? Are we good with that? How to do scalar multiples of vectors? Let's have a vector u. Now let's change who u is. Let's have u equals that guy. A scalar multiple would be 3u, 5u, a half u, minus 4u. These are all examples of scalar multiples. Okay, what do you think you do to find 3u or 5u or a half u or whatever? What do you do to the vector u to get these, what are called scalar multiples of it?
Multiply the x, y, and z by the number.
Right, so by the scalar. So this would be 3, 9, negative 6. This would be 5, 15, negative 10. This would be a half, 3 halves, negative 1. This would be negative 4, negative 12, 8. Would you agree intuitively that makes sense as well, isn't it? Now, if you imagine this is my vector u. If someone said, what does 3u look like? Won't it just look like the same, but 3 times longer? And wouldn't 5u just be the same? By the same, I mean parallel, right? Same direction, but 5 times longer. Wouldn't a half u, not sure who, yeah. Wouldn't a half u just be the same direction, but half as long? But wouldn't negative 4u have one extra difference that none of the others have? Do you notice what extra difference negative 4u has that the other vectors didn't?
Direction change.
The direction change. So isn't negative on a vector, if there's no other numbers involved, isn't negative on a vector just a direction change? So if this was a vector v, wouldn't negative v look just like it, but pointing the other way? I think these are going pretty good. I mean, some of it is, for some of you, it's, yeah, I know how to do this. I've seen it 100 times. And for others, it's maybe a little bit more necessary that I took the time to do that. So let's now look at what's called the magnitude of a vector. If you have a vector and it's called 3, 4, 12, then the magnitude of a vector is that. And the magnitude of a vector isn't it the length of u? Right, it's how long the vector is. Let me do a general version. If you want to get the magnitude, length of a vector, that's how you do it. There's your formula. The magnitude of a vector is the sum of the squares of its components. So if you want to find the magnitude of this vector up here, it's going to be 3 squared, add 4 squared, add 12 squared. Well, that's going to be 9, add 16, add 144, which is going to be the square root of 169, which is 13. Because the magnitude is a real physical number, won't the magnitude always be a positive number? You wouldn't expect negative magnitudes, right? Magnitude is a scalar, agreed? It's a number, it's a scalar. In this case, a positive scalar. Now, you will get answers that are nice, in which case we expect you to call it 5. You will get ones that are useless in the sense there is no way making them look pretty. But can't you also get those guys? They're not a perfect square, but can't you still simplify them? And you are expected, even if nobody tells you to do it, that you are expected to rationalize the guy, right? Make it look pretty. That seems reasonable. Keep away from decimals unless the question says specifically to 2 decimal places. So always assume that they want exact values otherwise. Let's put the whole package together and do some vector work. Let's have the vector A being 1, 2, 3. Vector B to be -1, 5, 1. And the vector C to be 2, 3, -2, because I want it to be, right? And you could be asked, and will be asked, to do vector calculations. So you might be asked to do A plus 2B take away 3C, right? Let's make that our first question then. Would it not be this vector plus that vector, right? Take away that vector. And 1, add that, take away that, is -7, I believe. 2, add that is 12, take away 9, leaves me with 3. 3, add that's 5, take away -6, gets me 11. And I hope that that's the correct answer. Definitely the method is right. Are we okay with that? I mean, it's just numbers adding, multiplying together things. Now, suppose they asked you to do that. Well, wouldn't you do this first? And then you'd find the magnitude of this. And so that would be that squared plus that squared plus that squared. That'd be 49, add 9, add 121. Square root 179. I'm not 100% sure, but I think that's one of those you can't do anything with me ones. So I guess that would be the answer. So pretend that was question B. Do you feel comfortable about the arithmetic of vectors? How you can add and subtract them and find their magnitudes? I'm getting lots of nods here. Are the nods because you've done this in so many other places that it's second nature now? Okay. Now, you could get your question like this. There's A. Let's just do a B this time. One of the reasons I do not like this notation is because I am careless. If somebody said to you, 3A, take away 2B, it's 3 lots of this guy. Take away 2 lots of this guy. So it's 3I plus 3K take away 4i, add 6j, take away 4k. And that guy and that guy gets me negative 1i. That guy doesn't work too well, goes with this guy, you get see, I almost did it. Plus 6j. Then you do this guy, negative 1k. So that's your answer. Why do I make mistakes in these? I almost did it there. If something's not there, do you notice you don't put the letter? You don't say 1i plus 0j plus 1k. Do you notice you just don't write something if it's missing? And I tend to, I don't know, it's just my brain. I tend to make mistakes, so I try and avoid that. Now, if someone went and said to you, find the magnitude of this vector, it's going to be this guy, negative 1 squared, plus 6 of this guy squared, plus negative 1 squared. Do you notice it's only the coefficients that get used, not the I, j's, and k's? So what do I get? I get a 1, a 36, and a 1, square root of 38. Yeah, pretty sure that's going nowhere, so that's the answer. Are we comfortable with adding, subtraction of vectors, scalar multiples, and magnitude? Do you feel comfortable with these types of questions? Anything you want to ask before we move on to our... Yeah, we've got enough time for it for our next thing. Last chance, are we good? Okay. For the last thing for today is how to find what's called a unit vector. So let's have a vector u, and it's equal to 1, 3, negative 2. And let's pretend that that's what u looks like. A unit vector is a vector in the, let's change that, vector that is parallel, that's a better phrase, that's parallel to u, but is 1 unit long. So can you imagine that that would be my unit vector? I'll call it v, right? Parallel, same direction, right? But it's only 1 unit long. So how do we calculate it? Well, you find the magnitude of u. So it's 1 squared plus 3 squared plus negative 2 squared. And that ends up being the square root of 14, which is as good as that's going to get. Then the unit vector, which I've decided to call v, is simply going to be that multiple of u. Does that make sense? That if you divide all the numbers by the square root of 14, because that's a scalar multiple, won't it be the same direction? And won't that square root of 14 get you a vector whose length is 1 because you're dividing all the numbers by that amount? So you would end up with 1 over the square root of 14, 3 over the square root of 14, and negative 2 over the square root of 14. And you can check that, but I bet you the length of that vector is 1. Can you kind of do it in your head? Isn't it going to be 1/14 plus 9/14 plus 4/14, which ends up being 1, and the square root of 1 is 1. So a unit vector is, if you want a formula for it, 1 over the magnitude of the vector u. We okay with that? You want a unit vector, just find the length of it and divide everybody. If I was being fussy, which I am, although WebAssign is not, would this be the best way to write that vector? When you have to do that rationalize the denominator thing. And so you would end up with, oops. There we go. You'd end up with that. Say your last name and bye-bye. I'll hang